Hello, chemistry students. In this video, we're going to go over titration and the theory behind that. In other videos and lessons, I have an assignment in particular. I have details that outline more on the skill and the lab skill that is titration. So for now, a bit of background and a bit on that skill. But before we actually do get started, here is a little bit on some practice on how to figure out the pH of a solution. Okay, so I have another program open here to answer this, but if you want to pause this, it's a good test to see if what you get matches what I have. And again, let me know if there are any questions, post comments, message me, and we can go over those questions and answers and other examples as well. Okay, so in this question, I'm going to toggle back and forth, right? We have, look at the question first, a certain mass value, right, certain mass value of H2SO4, and it's asking us to figure out what the pH of the solution is with a volume, or if it does have a volume of 150 milliliters. Okay, so as always, when you don't know what to do, and even if you do, always find the number of moles. Now the question gives you a mass, right? Molar mass of H2SO4. Quickly look that up in a periodic table, and you get approximately 89 grams per mole. We know that moles are equal to mass divided by molar mass, and we have 0.0012 grams divided by 89 grams per mole. And I did this calculation just before we started. It's 1.3483 times 10 to the negative 5 moles. All right, again, always try to keep it at least 4 or 5 digits after the decimal place. Okay, so that's how many moles we have. Remember, that's how many moles we have of H2SO4. Question's asking us, what is the pH? Now we know pH refers to the negative log of the concentration of hydrogen ions, not the concentration of H2SO4. So that means we have to take something into consideration. We have to look at the dissociation of H2SO4. Okay, so this in an aqueous solution will dissociate to look like this. We have two hydrogen ions and one sulfate. So if we figure out the number of moles which we have of H2SO4, right, 1.34 times 10 to the negative 5 moles, we need to go from here to here. Now, using some stoichiometry, we can use a factor label method, we can use a proportion method, or simply a since and therefore statement. We can say since it's a 1-to-2 ratio, then all we need to do is multiply this by 2. So if we multiply that by 2, since it's a 1-to-2 ratio, what we get is I'll write that down, okay, 2.6966 times 10 to the negative 5 number of moles of hydrogen ions. Now again, we're not looking for moles of hydrogen, we're looking for the concentration of hydrogen. Okay, we have then moles. To figure out concentration, we need moles divided by volume. Well, we have 2.6966 times 10 to the negative 5 moles. Now the question says that we have 150 milliliters. Well, convert 150 to liters, and we get 0.150 liters. So once you divide the two, you end up with 1.7977 times 10 to the negative 4 moles per liter. Okay, great. So now you have a concentration of hydrogen ions, and you are almost done. It's going to switch colors, but we can continue. It doesn't really matter. Okay, pH then is the negative log of the concentration of hydrogen ions, which we now know it's 1.7977. Again, try to keep at least 4 or 5 digits whenever you can. Oh, I wrote 5. It's negative 4. Okay, and we get 3.745 as our pH. Looking though at our original information here, looks like we have 2 sig figs, so I'm going to want to just round to 2. We get a pH of 3.7. Hopefully that answer matches what you figured out yourself. Okay, so that's the minds on part, or the let's review now that we're ready with that. This particular acid is actually going to be repeated in our final titration example. So there's a bigger reason why I have this example here than you might think. Okay, so here's your titration apparatus. I'll go over all of this now. So titration is essentially a lab technique that uses the precise concentration of a substance to then figure out the concentration of another, simply put. Now, in grade 11, we do strong acid, strong base titrations. So what you will usually find, but it can be flipped, but what you'll usually find is that in your burette, that's this long, upside down, graduated cylinder looking thing, you usually have your base in your burette, and that's called your titrant. It's what is being used to titrate, so it's called a titrant. Now that is horrible penmanship, but it's a titrant. Okay, and inside your Erlenmeyer flask is your acid. Usually, again, it can be a base, but usually for our purposes, it will be an acid, and this is called an analyte. Whatever is inside your flask is being analyzed. Its concentration is unknown. So since it's being analyzed, it's called your analyte. Now, these two can be, as I said, switched. You can have acid here, you can have base here. You can have an acid with a known concentration, and you can have a base with an unknown concentration. But for most of our examples, we're going to do a base in your burette and an acid in your flask. Okay, so what if you do drop a base into an acid? Do you know that we're going to get neutralization occurring? Okay, now here is where I would usually have performed a demonstration for you. Okay, now what happens inside that Erlenmeyer flask is you get neutralization. Now in that Erlenmeyer flask, it's really important to have an indicator. Okay, this indicator, we have several to choose from. Some are probably better than others, but if we want to neutralize that acid with the base we are dropping in from our burette, we're going to want to find an indicator that changes at about a pH of 7. So methyl violet wouldn't be a good candidate because that doesn't change at a pH of 7. It stays violet or dark blue. It instead changes at much lower pH values. Going across our different indicators here, we do come across maybe some that might be good. Bromothiamyl blue is a good one. Practically speaking, it sometimes is hard to visualize that green looking different from the blue and then transitioning then into the yellow. So it's sometimes hard to see, but that does change at an approximate pH of 7. I think it's 7.2 actually. But BTB or bromothiamyl blue could be a good candidate. We have phenol red that changes at a little higher pH, but that could be a good candidate too. Then you'll be surprised what we're going to use. We're actually going to use phenolphthalein. Phenolphthalein seems to be the standard indicator for most acid-base titrations, strong acid, strong base titrations. Now, it does look like it doesn't really change in this picture, but that might just be the quality of the picture, or it might actually be correct, because it does actually change into a dark pink at a pH slightly higher or higher than 7, actually closer to 8. So that makes this kind of titration a little bit tricky when we perform in a lab because we don't want it to be that dark pink color. We want it to be as close to 7 as possible. So we're going to use phenolphthalein in our lab this unit. Now here's where I would have shown you a video. I will post this video on as a separate link. It is a great video, and I'll give credit where credit is due. I'll post it in our class site with the original author's link. Okay, so again, neutralization is happening, and just to review that. So what you have here is sodium. I know this is already moved, but I'll pretend it wasn't. We have sodium from sodium hydroxide and hydroxide from that same base. HCl, assuming we're working with hydrochloric acid, and we have hydrogen ions and chloride ions. Now, they are going to interact. Sodium and chloride are your spectator ions not really involved in the reaction here. But what really happens, our net ionic equation then is the formation of water in this neutralization reaction. So this is what's really happening. Now, for this to happen all in a one-to-one ratio, as you one-to-one-to-one ratio, as you see here, we at a certain point, let me just change pens here. At a certain point called your equivalence point, the number of moles of hydrogen ions, right? 'Cause that's what's really involved here, right? Hydrogen and hydroxide. At that equivalence point, we have the number of moles of hydrogen ions exactly equal to the number of moles of hydroxide ions, and that's how you want to. That's what we really want at your equivalence point. You want a pH of exactly 7. You want this to occur mathematically, experimentally. Okay, and that's called your equivalence point. If you put a pH probe inside of your analyte and you measured pH at different points, you would see that pH doesn't change all too much as you begin titration, then it suddenly changes. So what that means is you will reach that equivalence point, and then very quickly you can titrate or over titrate to much higher pHs if you put any more base into it. So being very careful during this titration experimentally is key. Students usually find this lab quite exciting for that reason. So here are a few questions for you to think about. Already answered some of these, but if you can re-explain it to yourself or to someone else around you or just out loud to the world, then that means you understand what is going on. So here it is. What happens at the equivalent point? Right, we just mentioned that. What is the difference between equivalence and endpoints? I believe I mentioned the endpoint. I will talk about that again, so I might want to go back to this question. What can you say about the number of moles of hydrogen ions compared to OH ions? I guess the first and last question are kind of related. So let's talk more about endpoint in just a bit. Right, so again, equivalence point, this is the main idea. This is what you want to achieve in a titration experiment. Okay, now about endpoint. I knew it was coming up. So to begin, you slowly open up your Buret's valve and you start to drop base into your acid or titrant into your analyte, to be more general. Now, as the color begins to change, as you're reaching that equivalence point, you're going to want to slow down. So maybe a drop or two every second, and then slow down to a drop a second, and then just being very careful, try to reach that endpoint. It also helps, and I just realized now I didn't include this in our titration lab video, but if you can squirt a little bit of water along the sides, the mouth of that flask to get any remnants of drops of base to go into the acid, that's a great technique to make sure that you're being very precise. But I do believe the video that I will post does make reference to that. That's not the one I made, but the other one that goes over technique. So you want to reach an endpoint that is barely pink. Remember, phenolphthalein doesn't really change color until it's above 7, so you don't want it to be this color. This is over titrated. You've gone well above pH of 7. You want it to be barely pink. I usually say in class, if I can see that it's pink from across the class, it's over titrated. It's gone too far. Start over. If I have a hard time seeing that it's pink from across the class, and as I approach, it begins to look very slightly pink, then that's perfect. So that's the challenge in a titration experiment. Okay, our first example. So here we have, and there's a lot of information usually, so it helps to pull out whatever is relevant. So here we have 20 mils of HCl solution of an unknown concentration. All right, so in that flask, let's see if I can draw this. In that flask you have of acid, you have 20 mils of HCl. Okay, so we have volume. We don't know the concentration. So HCl concentration is not known. This is our analyte. Okay, there must be some indicator inside here. Then we requires 35 milliliters of that concentration of sodium hydroxide. So we have a volume of our base, right? It's 35 milliliters, and you're going to want to convert that 0.035 liters. We also have concentration of our base at 0.25 moles per liter. Okay, so what is the concentration then of that unknown solution, of that unknown concentration of acid? Okay, using all of this, just a little background before we actually get into work. Remember, a little analysis here. N number of moles of a solution is simply C times Z. So we have all the information we need to figure out how many moles of base. Okay, let's jump into this. So let's do that. So concentration times volume gives you that many number of moles of base. Now we know that the reaction, looking back, this is a 1-to-1, 1-to-1 to 1-to-1 stoichiometric ratio between all of our substances. So the number of moles of one is equal to the number of moles of the others. Now that we found the number of moles of sodium hydroxide, we can say that X is then the number of moles of HCl because it's 1-to-1, right? Therefore, that is the number of moles of HCl. Great, so we have moles of acid, but we don't necessarily need moles of acid. Well, we do, but our real what we're looking for here is actually the concentration of acid. That's what we do not know, but we know that concentration is moles divided by volume. So by knowing the number of moles, we're halfway there, over halfway there. Now divide then by the volume of acid, right? Volume of acid, 20 mils given to you in the question. Convert that to liters, and we get 0.44 moles per liter, and that is our final answer. That's a concentration of your acid, of your HCl acid. Okay, so this is employing a stoichiometry using mole ratios technique and solving for the unknown concentration of an acid in a titration experiment. In this next question, I could solve it the same way. I'm going to choose a slightly different way. It gives you the same answer. It's up to you to choose either way, whatever is easiest. Okay, so here we have 20 mils of an unknown concentration of acid. This time it's H2SO4. Remember how we solved an example using H2SO4 before we started talking about titration? Okay, well, this is why. Hopefully it'll help you out here. Okay, now that needs 35 mils of that kind of concentration, that sort of concentration of sodium hydroxide, so that we can reach that equivalence point. So what is a concentration of your acid? So it's essentially asking the same thing. What is the concentration of that acid? That's not known, so figure that out. But this is different. This is no longer HCl, that initial monoprotic acid. This is a diprotic acid, H2SO4. So let's go back, switch to, make a new page here. Okay, let's go ahead and solve for this. So when you don't know what to do, of course, it's always important, even if you do, always find the number of moles. So we're going to find the number of moles of hydroxide ions. And we know that the question gives us 35 mils or 0.035 liters. We're going to multiply that by its concentration given to you in the question. And what we end up with is 0.00875 moles. Now, at that equivalence point, we know that the number of moles of OH ions is equal to the number of moles of hydrogen ions. Therefore, this should actually be since. So since at equivalence we have this is moles, therefore the number of moles of hydrogen ions are equal to the same thing. Okay, now we need to look at how this dissociates, because yes, we know the concentration of hydrogen ions. We're not being asked for the concentration of hydrogen ions. Instead, look, it's asking for the concentration of the acid, not just the hydrogen ions. So we have to take that into consideration. We know that this is going to dissociate in a 1-to-2 or 2-to-1 ratio, right? That looks like this. So since we have now the concentration, right, of hydrogen ions, we can, using stoichiometry and mole ratios, we can figure out how many moles in a 2-to-1 ratio, in this case, in a 2-to-1 ratio, how to go from here to there. So to do that, all we need to do is we need to divide by 2. So let's do that. So we take, to figure out the number of moles of H2SO4, all we need to do is take that, divide by 2, and we end up with 0.004375 moles of H2SO4. And we're almost there now. Now that we know the number of moles of H2SO4, remembering also that we have volume given to us, it's 20 mils, we can now figure out finally the concentration of our acid, and that is 0.004375 moles divided by 0.02 liters, since we've converted that to liters, and we end up with 0.21875 as our concentration, big M, but we're going to round that to the nearest sig fig with 2 sig figs here. From the question, we get 0.22 as our final answer, right? So this still used stoichiometry, not in the same way as a previous answer did. Instead, we're using since and therefore statements, and we're using direct mole ratios and simply dividing where necessary. Okay, so hopefully that helps. It is important now for you to spend some time, right? We did this example, to spend some time then on the homework. Post any questions and I will get back to you as quickly as possible. Again, hope this helps.